go. First thing we're going to do is we're going to talk about just the 3 laws, Newton's 3 laws, just to remember what they were. The first law was the law of inertia, and it's the law that goes objects at rest will stay at rest and objects in motion will stay in motion unless they are acted upon by an outside force. So everything in this room will stay where it is unless we put an outside force upon it. All right? So exactly, Jules. So the calculators generally stay on the table unless they are thrown off the table by people trying to sleep, apparently. All right, so the first law, again, objects at rest stay at rest, objects in motion stay in motion. The key thing associated with this law is the concept of inertia, which, as Bill Nye famously taught us, is a property of matter. But most importantly, it is a property of matter that resists changes to movement. And this is a principle that we're all very familiar with, but that we sometimes get confused. So, for instance, I think we just overthink problems. You know intuitively that a baseball thrown at 90 miles per hour and a car going 90 miles per hour don't necessarily have the same properties, right? So a catcher can catch a baseball going 90 miles per hour with no problems. But a catcher cannot stop a car going 90 miles per hour with the same efficiency, right? It's just not possible because the car has a much larger inertia than the baseball. So since the car has a larger inertia than the baseball, it's much harder to stop. All right. Another key thing that they will try to that I notice a lot of the times people bring up to try to confuse the issue is rather than dealing I think that's intuitive. Like if I ask you that, you should automatically go, okay, car has larger inertia, it's harder to stop.
If it was a toy car.
Okay, toy car, maybe not. But depends on the size of the car.
Okay.
So
Smart
the
car.
thing they do to confuse the issue though is they say, oh, well, what if we're in space, right? By that same token, it's just as easy. It's easier to push a baseball to get it started rolling than it is to push a car and get it rolling, right? You could just slap a baseball and it would go flying across the room. But if you slapped a car, it's not going to go anywhere, all right? Unless you're the Hulk, okay? So maybe Captain America, I don't know. He doesn't have like the strong properties though.
Don't downsize Captain America.
Compared to the Hulk. Anyway.
Hulk is GOAT.
So the other thing is that they'll put it in space, and they'll be like, in space, what would be going on? Would it be harder to push a baseball in space than it would be to push a car, or would they be the same, or would it be harder to push the car? Well, since you're in space, you start going, oh, well, it's weightless, so the car has weightless, and the ball is weightless, so maybe it's easy to push both of them. But the fact of the matter is that it is equally difficult to push the car in space as it is on Earth. Uh-oh. Yay! All right. So it's equally difficult to push the car in space as it is to push it on the Earth. All right. So the second law is what proves that. The second law is that the sum of the forces on the object is equal to the mass times the acceleration. Sometimes we don't say the sum of the forces, sometimes we say the net force. But either way, the sum of the forces acting on the object is equal to the mass times the acceleration. And you can rewrite this as the sum of the forces divided by the mass is equal to the acceleration, or sum of the forces divided by the acceleration is equal to the mass. All right, the third law. Third law is every action has an equal and opposite reaction, okay? So it's the equal and opposite reaction law. The key thing that most people forget is the equal part of that. We're all prepared to admit that there's an opposite reaction, but we don't usually think about an equal and opposite reaction. And so like a common thing that they'll throw at you is two things where the result on each object is clearly not the same, and ask you which force was greater. So for instance, a mosquito slams into a car, which was the force greater on? And your instinct tells you the mosquito because the mosquito gets destroyed. But the actual answer is that the force was equal and opposite on both of them. It was an equal force that the mosquito applied to the car that the car applied to the mosquito. The mosquito just didn't handle it as well. All right? By that same token, when you're walking around at night and you stub your toe on the coffee table, your toe hurts and the coffee table doesn't appear damaged. But that's not because you applied less force to the coffee table than the coffee table applied to you. It's because your toe reacted less well to the force. All right, it was the same force. Your toe just handled it poorly, whereas the coffee table handled it just fine. All right, the last thing we want to talk about before we move on is a free body diagram. A free body diagram is when you draw all the forces acting on an object. So like right now, everybody in this room essentially has the same forces acting on them. Right? So if you lift your feet off the ground, we'll just make it simple so that your feet aren't holding any of your weight. But if you lift your feet off the ground, you have the force of gravity pulling you down, which is always equal to mass times 10. And you have the normal force of the chair pushing your butt back up. All right? So the normal force of the chair pushes you back up and keeps you from falling through to the ground. All right, what if we added some more forces in here? What if we, instead of just having you sit in the chair, I have you sitting in the chair, but then I decide I wanted to push the chair, okay? If I decided I wanted to push the chair and we're in a magical world with no friction, then it would be normal force, force of gravity, and the force of my push. If there is friction involved, which, let's face it, most of the time there is, you would have the force of friction pulling back the other direction. Okay? So you would end up having an up, a down, a side, and a side force. Important thing to note. If this object was, say, accelerating at 3 meters per second squared, you would not, I repeat, you would not put that in the free body diagram. The only thing you're concerned with in a free body diagram is putting the forces acting on an object. You do not put velocities. You do not put accelerations. You do not put momentums. Only forces. All right? Everybody cool with that? Questions?